problem 1 involving estimating expansion and contraction during the bridge construction. So you are working for a bridge contractor who wants to check the designer estimate of how much reinforced concrete will expand and retract at the abutment. As shown in that figure here, you are told that the expected average summer temperature during construction will be 60 degrees Fahrenheit. The bridge deck is supported by a continuous cast-in-place concrete girder of 455, so that is 455 feet, resting on the 2 piers and 2 abutments. So that you have here 2 pier and 2 abutment. So for support assumption, the bridge is simply supported at 4 points, as you can see there, 2 at abutment at both ends and the 2 piers in the middle. The expansion coefficients of concrete is 8, 10 power 6, 10 power negative 6 inch power over inch degree Fahrenheit. The expansion coefficient of steel is 7.3, 10 power 6 inch power negative 6 inch over inch degree Fahrenheit. So as you can see, what is the expansion coefficients that we learn in the thermal expansion in your mechanics of material class. And as you can see, one of the reason why we work steel and concrete working together, from the coefficient that you see here, they are very close together. So when the whether the temperature increase or decrease, they expand, the expansion for the steel and concrete are almost similar, and for contraction it will be almost similar, so that they can easy to work with. If you imagine the two material, one is the expansion coefficient very high, the other expansion coefficient very low, then when the expansion they don't work together, then the bonding between the two material can be compromised. So that not be ideal. But for the concrete and steel, as you can see here, the expansion coefficients are very same 8, 10 power negative 6, 7.3, 10 power negative 6. So they work very well. That's why it widely application of reinforced concrete in there. The next assumption, the maximum elongation at one abutment will be that caused by 1/2 of the bridge. So 1/2 will distribute it to the left abutment, and 1/2 the right, it will be distributed to the right abutment. Maximum long-term concrete temperature during winter, 37 degrees Fahrenheit. Maximum long-term concrete temperature during the summer in 90 degrees Fahrenheit. So let's work on this problem. The first, we need to check the temperature increase relative to construction with the permanent long-term concrete temperature during the winter, and of course we also have the temperature decrease relative to the long-term temperature. So let's do that here. First find out the temperature increase relative to construction. And that here you have the increase, so the long-term temperature during the summer in 90 degrees. During construction, the average is 60 degrees. So we have 30 degrees for the temperature increase. We also be able to find out the temperature decrease relative to construction. To construction. The long-term temperature in the winter is 37 degrees. So you have that, and the average temperature during construction is 60 degrees. So the degrees in here we have 60 during construction, Long-term temperature 37 degree. So you have that in 23 degree Fahrenheit. And with that increase, temperature increase, we have elongation, and with that decrease, we call it contractions. But there are two material, concrete and steel. Just like make a symbolic girder that you have here. That is girder, and you have steel. Just make a symbolic here. So you have that a rib steel. And of course that you have that here girder. Okay, so that concrete girder. From there, you can be able to find out the elongations and the contraction for each of the material. So first for concrete, we need to find out the maximum elongation of concrete. From there, we have the temperature increase, elongation for temperature increase. So you have 30 degree. For concrete, the expansion coefficient 8 10 power negative 6. So 8 times 10 power negative 6. And then the and per inch, power inch. So we have to time the length. And you recall the length of the girder in this case is 455. 455, and that fit. So we need to change to inch because this is inch power in for the thermal expansion. So you have times 12 inch over feet that you can see there. So with that we get 1.31 inch. And of course, with that temperature increase, we can be able to find out the maximum elongation of steel. And that you can do the same, 30 degree times 7.3, 10 power negative 6, 455 feet for the girder length, change to 12 inch over feet for the unit conversion, and from that we get 1.2 inch. So that the elongation. So as you can see, the more for the concrete elongates more, a little bit more in there. 1.31 inch compared to 1.2 inch. Similarly, we can be able to determine the contraction of concrete and steel. So we can have the maximum contraction due to the temperature decrease of concrete. Again, that the decrease 23 degrees, so you have 23 degree times the thermal expansion again, 8 negative 6, 455 feet, unit conversion. So you have that equal to 1.0 inch, and the maximum contraction of steel then we do the same, temperature degree 23 degrees 7.3, 10 power negative 6, the length of the girder 455 feet, unit conversion 12 inch, 10 inches over feet, so with 0.92 inch. And again, no surprise, concrete contracts more because the thermal expansion is a little bit higher, so you have that too. So what does the question ask? Now when we have all of that, the ask is the we check, right? Check the how the expansion during the construction. Okay, so that what the needed opening for that expansion at one side of the abutment. So from that one we have the needed opening at one abutment due to elongation and contraction, in this case of concrete, because concrete elongates more and contraction more, and that's what we should consider: elongation and contraction of concrete. So we just get the average between the two, because that is contraction and elongation. So the total for the concrete for the elongation is 1.31 inch, due to contraction 1.1. So on average we get, and this one, that is the total maximum opening for both sides. Maximum opening for both sides of the abutment have to be expansion and contraction have to be considered. But due to the assumption that you can see here, the bullet point number 4, the maximum elongation at one abutment will be that caused by 1/2 of the bridge. So from that we have to divide by 1/2 for one side, so that we'll have the opening at one side. Total opening that at the contraction and elongation, half we'll divide by 2. From that we will get 1.15 inch, and that should be the minimum requirement for during construction when we do with this bridge. And as you can see, you may wonder why how about steel? But then because the steel is encased in the concrete, so they will expand as one single components. And similarly for contraction, because they bonded together. So with that one, we are done for problem 1.